Well, hi, everyone. I'm Rick Wilson, the director of Scientia, and I'd like to thank you for virtually attending today's lecture. This year's series is entitled Trade-Offs, and trade-offs are always with us, whether balancing work and family, self and community, privacy and safety, present needs and future goals. Trade-offs are part of virtually every facet of human life. Well, this year, Scientia looks at the science, philosophy, ethics, economics, and art of the balancing acts that are so much part of the human condition. Since we decided on this topic, trade-offs have become even more important as we decide how to work around COVID-19. Well, today's speakers know a great deal about the trade-offs confronting people in the planet. We're particularly fortunate to have two wonderful speakers, both addressing climate change, trade-offs between people and planet. I'm going to introduce each speaker separately before they talk. Our first speaker is going to be Sylvia Dee, and our second speaker is going to be Pedram Hassanzadeh. So let me start with Sylvia. She's an assistant professor in the Department of Earth, Environmental, and Planetary Sciences at Rice University. She earned her BS at Princeton in Civil and Environmental Engineering with certificates in Geological Engineering and Environmental Sciences. Her PhD is from the University of Southern California Earth Sciences Department. She's held postdoctoral fellowships at the University of Texas Institute for Geophysics and Brown University. Rice was very fortunate to hire her in 2018. Sylvia heads the Climate, Water, and Energy Lab here at Rice. She's a climate specialist, a climate scientist, rather, specializing in atmospheric modeling, water isotope physics, and paleoclimate data model comparison. She has published numerous papers in journals like Science, Geophysical Research Letters, Paleooceanography, and Paleoclimatology. She's received several NSF grants and has been very active in organizing Rice's environmental community. Her efforts extend beyond the hedges. She's also been very active in bringing climate science to the Girl Scouts of America. Sylvia has agreed to speak for 20 to 25 minutes, and we'll reserve questions for both her and Pedram, our second speaker, after both have spoken. You'll be invited to ask your questions during the Q&A function anytime during the course of the talk. If you want me to ask your question, just write it out and I'll relay it to our speakers. Please use the Q&A function to queue up for the questions. I'm not going to be paying as much attention to the chat function. So without further ado, it's my great pleasure to introduce Sylvia Dee. Sylvia, take it away.
Thank you so much, Rick, and thanks for the opportunity to speak today on Scientia. So as Rick mentioned, I'm going to talk about climate change, which one can think of as sort of an ultimate trade-off between us and our planet. And I think it's usually good to start off by talking about how unique Earth is. Earth sits in an area of our solar system called the habitable window, where we're far enough from the sun for water to condense, and we're also close enough to the sun for water not to freeze most of the time. And so in a nutshell, Earth is the only planet in our solar system, and one of the only ones we know about, that's in what we call the Goldilocks zone, which can support life. And so we're very motivated by the habitability of our planet. And unfortunately, we do not have an experimental Earth. We do not have a secondary Earth, which we could easily travel to. We don't have a planet B. So this makes climate change a serious issue. When it comes to climate change, we know that the science is very simple. We know the impacts are serious, and we also are increasingly focused on the solutions to climate change. I'm going to talk through each one of these concepts one at a time. In terms of the science is simple, we know in paleoclimate in particular that our atmosphere has been in delicate balance for millions of years, and that humans are fundamentally altering the chemistry of Earth's atmosphere through our activities. In a nutshell, we know that we receive shortwave radiation from the sun, which heats up Earth's surface. We return that energy back to space in the form of infrared or long-wave radiation. And we have molecules in our atmosphere, specifically greenhouse gases, which act to absorb that outgoing long-wave radiation. You can think of greenhouse gases like a blanket that surround the planet. Our atmosphere keeps Earth warmer than it would naturally be. And so as we're adding additional greenhouse gas concentration to the atmosphere, we're essentially increasing the thickness of that blanket. In a natural greenhouse effect, heat escapes to space through the atmosphere, despite the fact that some greenhouse gas concentrations are here. A lot of heat is re-radiated back to the surface of the Earth. And again, the greenhouse effect keeps Earth at a habitable temperature. The issue is that we are now experiencing a human-enhanced greenhouse effect, where we're increasing the concentration of constituents like CO2, methane, and nitrous oxides, which causes a situation where less heat escapes to space. Adding additional greenhouse gases to the atmosphere can be thought of as getting a bigger sponge in the atmosphere or a taller goalie. Essentially, we're just absorbing more heat in the atmosphere and re-radiating it back to the surface of the Earth. We're preventing energy from being returned to space. The outcome of this enhanced greenhouse effect is measurable. This is global temperature change from 1850 to 2017. We know that the last 3 years have been similarly hot. These are temperature anomalies, so blue colors indicate colder conditions, red colors indicate hotter conditions. And particularly over the last several decades, we can see there's been a clear trend towards increasing temperatures. And again, this is a very simple prediction based on atmospheric chemistry and physics. And frankly, it's not surprising. We know that the total metric tons of carbon per year we've added to the atmosphere is increasing over time at a nonlinear rate. So the black line here is the total million metric tons of carbon that humans have released to the atmosphere per year. And in climate science, we typically talk about the change in the heat budget of the planet in terms of a unit of watts per meter squared. So if you've ever installed a 60-watt light bulb, right, watts are just a measure of power. And so the total radiation that's retained as a result of human interference is about 3 watts per meter squared per year. So again, thinking back to that 60-watt light bulb, 3 watts per meter squared might not seem like a lot. It's about the energy released by a poorly lit Christmas tree to its meter squared on the ground. But if we take the entire surface area of the planet and we add up those 3 watts per meter squared per year, because Earth is very large, that 3 watts per meter squared translates into the same amount of energy released by about 4 atomic explosions per second. So we are doing quite a lot to alter the planetary energy balance of Earth just through human activities. We're using the atmosphere as a dumping ground for excess CO2, but coming back to our theme of trade-offs, many would argue this is with good reason. Fossil fuel-based energy has given us modern medicine, right? We can see now with the pandemic, plastics, ventilators, we need fossil fuel-based products to provide all of this technology, transportation, air travel, water treatment, climate-controlled buildings. Every aspect of our modern lives in developed nations has been built upon a fossil fuel-based economy. So our world has become better for many, but at what cost? So we're focused on the trade-offs. What are those trade-offs? There are 2 prongs of trade-offs. One is consequences for the planet, and then secondly, there are consequences for us, the people. The first and most obvious trade-off is that the planet is warming, as I mentioned earlier. This is global average temperature change over time from 1850 through today. We know that surface temperatures are rising. We know that surface temperatures are rising more rapidly at high latitudes, specifically at the poles. This is a graph showing the change in Arctic temperature compared to global mean temperature change, which is just over 1 degree Celsius. The Arctic has warmed by about 5 degrees Celsius. This decreases ice cover in the Arctic, which accelerates warming. This is a graph showing monthly Arctic sea ice extent. This is an outdated figure. Arctic sea ice extent has essentially fallen off a cliff in the last 10 years. This is an animation showing the loss of Arctic sea ice since 1984 as a function of sea ice thickness. So this animation shows the stark decrease in Arctic sea ice, which again affects Arctic ecosystems, but also the reflectivity of the planet. Ice sheets reflect incoming solar radiation. So as we reduce ice cover, we accelerate the planetary warming. This is called the ice albedo feedback. Glaciers are also retreating globally. This is a graph showing the total length of glaciers in many regions throughout the world. And unsurprisingly, again, we've experienced dramatic ice mass loss. We also know the oceans are warming, actually containing much more heat gain than the atmosphere. And as a result of that, uh, partially due to thermal expansion, sea level is rising. This is the global average sea level change in inches since 1880. Satellite data and tide gauge data tells us that that increase is about 8 to 10 inches so far. Sea level is projected to change by up to 4 feet by 2100. And just for reference, the projected change in sea level rise for Galveston is about 6 feet, and that is the elevation of Galveston. So, what are the trade offs to planet Earth due to our dependence on fossil fuel energy? The answer to that question is that we have multiple independent measurements that show us that the atmosphere, land surfaces, and oceans are warming. The impacts of these planetary changes are serious, and the trade offs for people like us are enormous. One of the trade-offs that affects us directly here in Houston is more frequent. We've one of the most active hurricane seasons this year. As I speak to you today, Hurricane Iota is bearing down on our neighbors in Central America. And this is an animation of Hurricane Delta. We just narrowly avoided getting hit by major hurricanes this year. And Texas has already experienced 55 flood-related major disaster declarations since 1978. The rainfall accumulation for these storms is increasing. This is a picture from the intersection of Memorial and Shepherd from Hurricane Harvey, which many of you probably experienced firsthand. I'm not really sure why this gentleman is smiling because Harvey cost Texas about $125 billion and counting. We also know that alongside increasing frequency and severity of storms, drought and heat waves are projected to worsen, which Dr. Hassanzadeh is going to talk about at length. So this is a late 21st century projection for temperatures in Texas and the change in the number of days exceeding 100 degrees. As you can see, no matter how much carbon we emit to the atmosphere, whether it's a lower scenario or a higher scenario, we're looking at about a month to 2 months of additional days in many areas of Texas exceeding 100 degrees, which has profound impacts on people who work outside, for example. We're all acutely aware of the trade-offs that our fossil fuel dependency has on ecosystems, not least of which is major oil spills that have happened over the last 50 years or so. And unfortunately, my colleagues who study biodiversity at Rice would show us that the extinction rate on Earth is rapidly increasing. So this is the extinction rate that we've reconstructed from the fossil record in the past. And this is a log scale of extinctions per 1,000 species per millennium. The recent past falls at about 100 extinctions per 1,000 species per millennium. But in the future, the extinction rate is projected to be about 10 times higher than that current rate. Climate change is not the only problem that exacerbates biodiversity, but it is a major complicating factor. A common misconception that I hear a lot about climate change trade-offs is, well, that doesn't happen where I live. But unfortunately, I think that especially in the US, we've had a bit of a crash course on the direct impacts to us in terms of climate-related natural disasters, whether it's increasing risk of wildfire on the West Coast or in the Rockies. Tornado prevalence is increasing and tornadoes are getting more strong. Flooding is increasing. There really aren't that many places in the United States where you're immune from the trade-offs which directly affect human life. So given these stark impacts, one of the key questions that motivates my research is how much worse are these disasters likely to become in the future? However, answering that question is not trivial. I showed this figure earlier with Earth in a test tube. We don't have an experimental Earth, as I mentioned. But Earth science is also quite different from our colleagues, potentially in biology or chemistry, where we can set up a straightforward lab experiment. We can't do that in Earth science because we don't have a miniature perfect Earth. So the best approximation that we can use to answer this question, how will natural disasters change in the future, is to use climate models or general circulation models. And these models provide the only means for predicting future climate. And my research and my lab at Rice focuses on using climate models to look at future trends in some of these trade-offs. When we run climate models through the 21st century, we can get a pretty strong picture about how variables such as temperature, precipitation, wind speed, and even changes in storm frequency will change in the future. This is an animation showing changes in temperature under a high greenhouse gas emission scenario through the 21st century. You can see this amplified Arctic warming that occurs at the poles. And climate model projections specifically for temperature have come a long way and are giving us results that are actually coming true a lot sooner and a lot faster than we projected. Unsurprisingly, climate models project substantial warming beyond that which we've already seen over the last several decades. This figure shows the temperature anomaly relative to the late 1800s on the y-axis and the cumulative total CO2 emissions added from 1870 in gigatons of carbon. The black line here is the historical change in temperature. Again, it's about 1 degree Celsius through 2010. Each one of these colored lines represents a different emission scenario based on economic projections for how humans behave. So this dark blue line represents a massive effort to curb emissions, whereas this red line represents a business as usual or a immense growth in our carbon emissions over the next century. So obviously the temperature changes between we do a lot and we do nothing are substantial, and they're on the order of 3 to 4 degrees. I'm interested in the question, what is the impact of this warming on extreme precipitation and flooding in the United States? One of the major trade-offs that occurs as a result of human interference with the atmosphere is impacts to the hydrological cycle. As I showed earlier, water-related billion-dollar events are increasing in frequency. So these are tropical cyclone or flooding events from 1980 to 2017 or so. And also the cost of those events in billions of dollars from NOAA. These increases in costs and the increases in the frequency of these natural disasters is not surprising once again. We know that as we warm up the atmosphere using basic thermodynamics, it can store more water vapor. So anybody who's spent a summer in Houston knows that hotter temperatures mean more humid conditions. Okay, so we're already seeing the impacts of climate change on the hydrological cycle. They're upon us now. But as we continue to warm up the atmosphere, the projected change in precipitation falling in the top 1% of flooding events is likely to increase by 30 to 40% by 2100. One of the key regions I've been studying is the Mississippi River, which is a crucial economic artery for the United States. This is a Landsat or satellite image of the lower Mississippi River basin from October 2010, and then from the floods that occurred in spring 2011, which were absolutely catastrophic. We know that these Mississippi floods have been happening more frequently, and unfortunately, the magnitude of these flooding events could be worse in the future. We can investigate how much worse by using climate model simulations, and that's exactly what we're trying to do. Just this past year, in 2019, the Mississippi River had another year worth of really elevated flood discharge. This is a picture from St. Louis. These floods broke records and are generally the most damaging anything the Mississippi Basin has seen in the last 25 years, and really only bear passing resemblance to floods of the far distant past. But a lot of people, a lot of hydrologists and climate scientists now are asking the question, are these floods the new normal? And so what we've done is run climate model simulations using those different emission scenarios into the future to try to look at how Mississippi discharge might change. And this is work I've been collaborating with geomorphologists in our department, Kieran Dunn and Jeff Nitrauer. And what we're looking at is in different emission scenarios, how does lower Mississippi discharge change? So these two graphs are showing for different time periods of the 21st century, the probability density functions for the end of the century, the mid-century, and then the beginning or the historical period in red. What you can see is that the probability density function shifts to the right, indicating that by the end of the century, discharge statistics are moving towards elevated flood discharge values. So on this bottom left graph, again, this is the historical discharge on the Mississippi River. This red line represents our business as usual, high emissions, high CO2, humans don't get their act together, and the discharge rates go up fast and non-linearly by the end of the 21st century. By contrast, this blue curve shows the average of the model simulations in a mitigation scenario where we do curb carbon emissions. And just for reference, the design flood for the Mississippi flood control infrastructure is somewhere around this value here. So what we're finding is that climate model projections show that the difference between mitigation and no mitigation results in the difference between catastrophic infrastructure failure for the flood control system in the Mississippi River. So this is a crucial sort of, I think, communication point that needs to be stressed. If we do nothing and we continue to emit carbon at the rate we are experiencing now, we are setting ourselves up for extremely high costs down the road. The other problem that my lab has been working on more recently using climate model simulations is coral bleaching, an uplifting topic. And I apologize, but I'm going to get to the uplifting message in just a minute. We know that rising sea surface temperatures are doing major damage to coral reefs around the world. There have been die-offs of up to 70 to 80% in the coral reef barrier reef. And unfortunately, this has massive cascading effects for fisheries, tourism, you name it. Coral reefs are the bedrock of marine ecosystems. So we've been looking specifically at coral reef vulnerability in the Gulf of Mexico. Some of you may not know that the Gulf Coast is actually home to a great variety of reef organisms. And so we're trying to use climate models to understand how fast sea surface temperatures are likely to change in the future and whether there are pathways for us to mitigate these changes and at least communicate this directly to policymakers, because these reefs support billions of dollars worth of tourism and other economic benefits in the Gulf of Mexico. My postdoc, Allison Lawman, is doing this work now. She's just arrived at Rice, and I'm really excited to see what comes out of this. Just some final thoughts before I turn it over to Dr. Hassanzadeh. When we come back to the key message of trade-offs, my main message to you here, and I am not an economist, but anybody can see, looking at this map, that climate change is expensive. It's not expensive 50 years from now, it's expensive now, and we can save a lot of money by investing now. Unfortunately, Texas is winning the race in terms of the number of billion-dollar weather and climate disasters. Okay, we've had the most of any other state over the last 30 years or so. All of this data is publicly available over the NOAA website. And the uplifting message here is that we know this problem is solvable. So an example that I like to give my students is the example of the ozone hole, right? We knew that CFCs caused destruction of the ozone hole. The companies that were producing these refrigerants, which we need for our lifestyle, right? We need refrigerants, created a substitute that worked just as well as CFCs, and the ozone hole recovered. The Montreal Protocol, which was a global organization, a global policy agreement to curb the ozone hole destruction, worked. We can do the same thing with our energy production. Our modern day life, yes, we're dependent on energy, but it doesn't have to be fossil fuel-based energy. Renewable energy needs to be scaled up, and this is already happening in the private sector. Texas is the leader amongst any state in wind production right now. So we just need a new solution for energy production so that we can maintain our incredible technological developments that are helping us maintain our quality of life and bring other countries to the same place that we are. We are poised to drive our very sensitive climate system into unknown territory. Some of you may be familiar with the Edward Lorenz butterfly effect. So imagine that we're circling in a climate system on this side of the butterfly in a chaotic system. It's possible that at any given moment we could circle into a very different mean climate state. And so this tipping point is really something that is alarming, frankly, to many climate scientists. And we're going to have an all hands on deck approach for how we deal with these trade-offs moving forward. So next, you'll hear a little bit more about the specifics on changes in extreme events from Pedram. And I look forward to talking with all of you in a few minutes and answering all of your questions. Thank you very much.
Well, thank you, Sylvia. We'll come back to you for questions in a bit. Our second speaker is Pedram Hassanzadeh. the assistant professor in the Department of Mechanical Engineering and the Department of Earth's Environmental and Planetary Sciences. Pedram received his BS from the University of Tehran in 2005 and his MS from the University of Waterloo 2007, and PhD from UC Berkeley in 2013, all of these in mechanical engineering. He was the ZIF Environmental Fellow at the Harvard University Center for the Environment and a postdoctoral fellow at the Harvard University Department of Earth and Planetary Sciences. He joined the Rice faculty in 2016. Pedram is the director of the Environmental Fluid Studies Group here at Rice, and his work focuses on turbulent flows and chaotic dynamical systems in complex natural phenomena and engineering systems. Examples of the problems of interest are environmental and geophysical flows, extreme weather events, to which Sylvia alluded, including heat waves, hurricanes, atmospheric turbulence, and climate modeling. He's published in a variety of journals ranging from geophysical research letters to Nature Communications. His research has been supported by NASA, NSF, the Office of Naval Research, National Academy of Sciences, Microsoft AI, and many others. Pedram is going to speak fairly briefly, about 10 minutes, 12 minutes, something in that order. And again, you're invited to ask your questions using the Q&A function anytime during the course of the talk. I'll moderate it by calling on you and unmuting you so that you can ask the question if you'd like, or I can ask the question and relay it to our two speakers. So please use the Q&A function. And with that, I'll turn it over to Pedram. Floor is yours. Thank you.
Great. Thanks for the introduction, Rick, and thanks for the opportunity to speak here. So Sylvia very nicely talked about some aspects of climate change and putting basically the trade-off between the planet and the people in this context. What I'm going to talk about briefly is more about extreme weather events. That's where we are going to see the worst impacts of climate change. And it's very likely that we have already seen the footprint of climate change in some of the extreme events that we have had in the past decade or so. So let's start with a simple concept. So many of you have heard about the Paris Agreement, where the goal is to keep the increase in the global average temperature below 3.5 degrees Fahrenheit. Now, many people might look at this and think that, well, 3.5 degrees Fahrenheit is not that bad. It doesn't seem that awful. Houston, many days you have like 95 degrees. It's becoming like 98, 99. It's not the worst thing in the world. But there is much more into this issue. So let's just think about the PDF, the probability density function of temperature that is shown here. So here, this is temperature. This is the probability of the occurrence. And here, this line, the solid line, let's say this is what we currently have. And we have some days that we might get hot weather, some days we might get cold weather. With climate change, we know that the mean temperature would shift to the right. So as a result of that, if you look at the tails of this PDF, we'll see that already there might be a factor of 2, 4, 10 increase in the probability of getting more extreme hot events, more heat waves. But that's not the whole story. Climate change can also change the variance. It can change the variability of temperature. So now, even without changing the mean, if the variance of temperature increases, again, we are going to see a higher chance of getting more heat waves and even cold events. Even this is not the full picture. With climate change, we might also change the skewness and even higher moments of this PDF. For example, we might get a fatter tail on the right end of this temperature PDF. So you put all these effects together, from the change in the mean toward the hotter temperature, increasing the variance, changing the skewness, you might see increases in the likelihood of heat waves by factors of 10, 100, and even more. Now, you might ask, well, how can climate change, which many people just think of it as global warming, can change the skewness or the variance of temperature? Well, the issue is that our climate system is not just about temperature. We also have winds. And these are not winds that we see near the surface. These are winds that are extremely strong, on average 60, 70 miles per hour, that are the strongest near the tropopause, around 10 kilometers in the atmosphere. That's where the commercial planes fly. And this temperature, the wind distribution and the temperature distribution are closely coupled together because of what we know as buoyancy. And now, as Sylvia pointed out, with climate change, we are going to get a higher rise, faster rise in temperature for example, in the Arctic. And as a result of that, changing the temperature is going to change these wind patterns as well. Now, if you look at these winds, we'll see that they have a lot of variability. And we know basically these oscillations as the weather system. This is the high, low pressure system that we see in the weather news. And generally, they move to the east. But sometimes some of these high pressure systems, they basically stall, they become very large and strong, and they can cause all sorts of extreme events. These are called blocking events. Now, just to give you 2 examples, there was a blocking event over France in 2003 that was very deadly, very destructive, and it led to the hottest European summer in 500 years. So here, this is the temperature distribution for European summers from 1500 to 2009, and this is where 2003 was. Just 7 years later, there was another blocking event, one of these stalled high pressure systems over Russia that caused another very deadly and destructive extreme event. It even broke the previous record and made 2010 the hottest European summer. So these blocking events can be very destructive and very harmful. So there has been a lot of interest, for example, to understand how some of the characteristics of these blocking events, like their size, their frequency, their durance, the duration might change with climate change. So that's where I come in. So my background is in fluid dynamics, in mathematical and computational modeling. And in my PhD, I did a lot of work on some theoretical problems. And in my postdoc, I realized that there's a lot of demand for these kind of skills in the climate science community. So what I've been working on is really the fluid dynamics of extreme weather events. And the work that we do in our group is about combining theory, computer models, and observational data. And when it comes to computer models, we are not using only the big computer models, but we are also going all the way down to, for example, the Lorentz system, just a couple of ordinary differential equations that Sylvia already mentioned. And we build a hierarchy of models from ODEs, PDEs, idealized models, all the way up to the very complicated climate models and observational data. And what our group does is trying to understand things across this model hierarchy, because only then we can really trust that we have an understanding of the system. This is something very useful to look at extreme weather events, because extreme events, well, we like to understand them in observational data and in the big models, but by definition, extreme events, these are rare events. These are infrequent. And to get a good signal to noise ratio about them, it's very hard to have that from observational data or big models. So it's sort of important to build simpler models and then try to connect the understanding here to what's observed here and basically cycle through this. So to give you an example, in our group, we have been working on understanding some of the changes in these blocking events under climate change if we follow some of those scenarios that Sylvia showed and keep pumping CO2 into the atmosphere. So in a paper that recently was published in GRL, my student basically showed that the big models showed that the size of the blocking events are going to increase under climate change by at least 20%, which might not seem like a big number, but again, remember that these events are all about what's going on at the tails, and changing in characteristic of blocking events, even by something like 20%, 10%, can have a big impact on the extreme events that we see. But this is something that we found in the big models. And again, a lot of people are skeptical of the big models. I already saw there is a question there for Sylvia about the models. So we built a hierarchy. We went to very simple set of equations that still represent some of the characteristics of the atmosphere. And we built using what's called the Buckingham Pi theorem, a method that is a systematic dimension analysis technique. And we found a scaling law for the size of these blocking events. Now, this technique is something that has been around for a while. It's used a lot by engineers, for example, to find the scaling laws between the measurements that we do on a prototype in the lab and a real world object. This is how these kind of objects of extreme scales are designed. So we use the same concept, We found this scaling law. I'm not going to go through the details of exactly what it says, but then we saw that by this simple equation, we can explain the behavior we see in the big models and all the way in the models that are in between them, which brings a lot of confidence in what we are saying about how the size of these events would change with climate change. Now we are doing more work on understanding other aspects of how the blocking events would change with climate change. So I've been working on blocking events mostly because of heat waves since my postdoc. But when I moved here, just after a few months, we had Harvey, and I was sitting at home, and that was my first hurricane. It was an interesting experience. We started seeing in the news that when there's all this talk about, well, Harvey is not moving and it's stalled. And the reason is that there is this high pressure system sitting here over Western US, and this is basically a blocking event. So literally, the second day of Harvey, my friend Lawrence Young, who is an assistant professor in Earth Science department, sent an email and saying, hey, why this thing is not moving? Maybe we should look at this. And so we started pulling out the data and studying this problem that after 3 years led to a paper that we published. In the meantime, other people started looking at this. For example, there is a paper from MIT showing that climate change will increase the odds of Harvey-like rainfall by a factor of 20. So by the end of the 21st century, which is something really substantial. Again, this is because we are looking at the tails of the precipitation distribution here. So this was a study based on a single model. And again, we wanted to go back and build our hierarchy and try to better understand how much confidence we have in this kind of projection. So that's the work that, again, we started during Harvey and resulted in a paper that was published this year. So to do this, we first looked at some of the past hurricanes. So Harvey, again, famously, it was very slow moving. Here, these dots show each day where the hurricane was. So Harvey was around Texas for 5 days, and we got a lot of rain out of it. Allison was another storm that was also stayed around Texas for 5 days. And before Harvey, that was the record-breaking rainfall over Texas. And then in contrast to this, we had Ike, which basically moved really fast across Texas in just 1 day and didn't get much rain out of it, but we got a lot of damage from the wind and from the surge. So we started looking at how the atmosphere looked like during the time of these 3 hurricanes. And we saw that, yes, during Harvey and Allison, we had these high pressure systems over Western US that would stop a hurricane from moving. So this is basically what you see here, that's the storm. And we had the opposite condition during Ike, which basically pointed out to us that, well, this is a good way to try to understand this problem. We started looking at models, not one model. We looked at models from NCAR, from NOAA at Princeton, from Max Planck in Germany, average of 15 models. And here what's plotted, this is the northward wind over North America and how it would change by 2080 versus 2005, again, following one of those climate change scenarios that Sylvia showed. And we'll see that, the models have different projections for some areas, but if we look at Texas, we'll see that it's always red. We see this very robust increase in the northward wind over Texas, which suggests that the hurricanes are actually going to move like Ike rather than Harvey or Allison when they get close to Texas. Again, we are never drawing conclusions from a single model or a single approach. We have done a lot of work over the past 3 years looking at different types of data, comparing these models with observations to see how good they are, and also teaming up with a group at Columbia University to use a different approach into looking at hurricanes. And again, I'm not going to do the details, but here, this is a PDF of the speed of the hurricane when it comes near Houston, basically in the radius of 300 kilometers around Houston. Red is with climate change at the end of the 21st century, or really year 2080. Blue is the current climate. And you'll see that under climate change, the frequency of slow-moving hurricanes would decrease, and the frequency of fast-moving hurricanes, the ones that move like at 25 kilometers per hour rather than 5, that would increase, which our results, again, looking at over 20 models, thousands of years of simulations, 3 different approaches showed that climate change will increase the likelihood of faster moving Texas hurricanes by a factor of 4. Again, we might very well get hurricanes like Harvey that stall, but the likelihood of faster moving hurricanes would increase. And again, going back to the idea of hierarchical modeling, we have done more, and I'm not going to go to details, but what we understood, again, based on very basic physics, is that what would control the movement of future hurricanes over Texas is not about those blocking events in the high latitudes, but really is about remote changes over the Bermuda Island and also over a region that's called the North American monsoon region. And these two changes together would reinforce each other over Texas, and thus that's why we had such a robust response over Texas. So this is my last slide. So what we found in our research is that blocking events are going to get bigger, which suggests that the future heat waves are going to cover larger areas, are going to impact many more people. In terms of the hurricanes over Texas, we are finding that we are going to have an increase in the likelihood of faster moving hurricanes. Now, faster moving hurricanes are not necessarily good news. If we look at the most expensive hurricanes and Atlantic hurricanes in North America, we have a slow moving hurricane like Harvey, and we have a fast moving hurricane like Ike. They both affected Houston. So it just says that the way that we are going to come up with adaptation and mitigation plans, it should just be different depending on whether we are going to get more slow moving or fast moving hurricanes. And that's the direction that we are moving, and building collaborations at Rice and other places to look into these problems. So to wrap up, what I'd like you to remember from my talk is, first, extreme events are going to change with climate change. Many of them, many aspects of them are going to get worse. And this understanding is not coming from a single model and a single approach. Climate scientists really know what they are doing, and we are really building multifaceted approaches based on different types of data sets, different types of skills. We are building more and more rigorous mathematical frameworks to look into these problems, and they're all pointing into the consistent direction. So with that, I stop, and I'm looking forward to your questions.
Thank you, Pedram. Both you and Sylvia paint a scary picture with your models and with your data. And a number of people have commented on that in the Q&A. And a lot of the questions are about the trade-off between fossil fuels and renewables, and whether those trade-offs also can take into account the fact that people are not all that interested in trade-offs that cost them something. So the economics behind either moving purely to renewables, in the short run, is problematic for some. So that seems to be one question that's being asked. So I'll throw the political questions to you a little bit later, since that's the thing I enjoy doing. So if either of you would take over that.
I guess I can go first, but I'd love to hear from you, Pedram. I mean, I think the key here, I'm going to punt a bit and say that I'm a natural scientist and not a political scientist. Like I mentioned, this is an all hands on deck problem. We need people who have expertise in climate economics and climate policy to be working to get a good handle on the true cost of lack of action. Regarding renewables, there are a couple of questions about needing to have a concrete plan. I would argue that many of the presidential candidates, including the president-elect, has an actual very actionable plan for implementing and upscaling renewable energy. And in particular, that plan does talk specifically about regionally targeted upscaling of renewable energy, right? It doesn't make sense to put solar panels in New England. It doesn't make sense to put wind farms in places that it's not windy. There will be massive changes to our transmission system that are required, but yeah, all of this stuff is going to cost money. But the example that I showed, for example, with the Mississippi River, this is a choice that we have, right? It's the choice between spending money now so that we don't have catastrophic flooding every year after 2050, resulting in the failure of the Mississippi River flood infrastructure. So, do we spend money now or do we spend money later? That's a question of environmental ethics that I can't really answer. My job is to provide the best, most accurate science that I can so that policymakers can make these decisions. And so I guess I don't know if that answers part of the question, but Pedram, do you have more to add about the costs?
I think, again, so that's something beyond my area, my expertise. And I think there's a lot of opportunity for work between climate scientists, people who work on natural hazards, and economists. And this is something that to some extent we have started at RISE. So one thing I wanted to mention that even extreme events and things like that aside, even these changes in the wind patterns can affect the wind energy. And I mean, Texas is the biggest producer of wind energy. And this is something that we are going to invest in more. And there should be some work on understanding how these, we are going to design the wind farms based on the current understanding of where the winds have been historically, but there are going to be changes. I know people in UK have been already like thinking about these kind of problems. And I think something particular to Texas, I think we should think about more, because it's just amazing that how much climate change, again, is not just changing the temperature, that winds are going to change regionally and also globally. Again, I mean, also there are a lot of other good questions here. There was one question I like to answer is, do your models have results on the hurricane intensity? So that's a great question. So we were very lucky with the question about the movement of the hurricanes. We found these very robust results. The results are not so robust with respect to the category. So our collaborators at Columbia, they already have a paper. It's not clear how the strong hurricanes that would make landfall in Texas, how they would change with climate change. And we have a proposal actually led by Jamie Paget, and kind of to extend that collaboration to specifically answer that question by, again, building more models and doing more analysis. So I want to answer that question.
So Richard Johnson asks whether you see proposals that are floated to do carbon sequestration, pulling it out of the atmosphere and dumping it elsewhere into the ground, pumping it underground, something. Do you think that's going to have much of an impact in the long run or even in the short run? I mean, most of your models are talking about the short, we're facing serious short run problems, not just the long run problems. Who wants to take that one?
So again, that's something beyond my area of expertise. I also wanted to mention that a lot of people thinking about geoengineering by adding sulfur to the stratosphere. And some of those ideas, again, people are looking at them seriously because they realize that if we just follow the business as usual, at some point by 2070, 2080, we will have a lot of problems. So certainly there are a lot of ideas out there to do a cost-benefit analysis and see the cost of these ideas and how much we can control the carbon. I think that's something to do. Again, it's beyond my area of expertise. I don't know if Sylvia wants to add.
Yeah, so many of our colleagues at Rice are working on various methods for carbon dioxide removal. My colleague Jonathan Aho Franklin, who's a geophysicist, is working on carbon sequestration and the geophysical issues related to that. As far as I know, there is not a method that works well that can be used to remove CO2 from air. Once it's already there. The other issue with both carbon dioxide and methane is that they have very long residence times in the atmosphere. So every molecule of CO2 that we've emitted already is there for the next 400 years. So you have the issue of committed warming. So I wish that I was more up to date on the air capture technology, and some of our colleagues in engineering might be able to update us all on where that technology stands, but I haven't seen anything about it recently.
So Pedram, one of the things that you mentioned was maybe doing some kind of reflective pumping of things into the troposphere to bounce off solar radiation to help slow down warming. Certainly some of your models would be of value in such a setting. How much confidence do you have in your models, and how much confidence do you have that maybe we could get the right estimates if we chose to actively interfere in the troposphere?
Yeah, that's a great question. So when I was at Harvard, actually Harvard was the Center for the Environment was building a big group of people from different disciplines to work on this geoengineering problem. And I've seen papers coming out looking at all sorts of models, very simple models to just for example, as Sylvia mentioned, like changing the optical depth in the atmosphere and see what the impact would be, all the way to using very complicated models. We are now building better models that are doing a great job in the chemistry in the stratosphere. That's where these aerosols are going to be. I think globally we can have good estimates of by how much we can cool, like some related to some work that Sylvia has done. We know that from volcano eruptions that there is going to be global cooling. And so it has a similar effect. I think the challenge is at the regional scales, predicting climate change, natural or forced, regionally, that's a major issue. And so my concern is that at some point we decide to do some geoengineering, and then every country would have their own kind of ideas of how much impact they want to get from climate change, from this kind of geoengineering. And also it would be very hard to model that. Generally, regional predictions are very, very difficult. So we were very surprised that in our work with the hurricanes, we got some robust regional responses, but generally regional responses are difficult. So that would be the main challenge, because the impact is not going to be uniform.
Sylvia,
Yeah.
did you want to add anything?
Oh, I just to echo that in terms of, right, I guess geoengineering or purposeful alteration of the climate system. Yeah, a lot of the work my lab has been doing is looking at volcanic eruptions as analogs for sulfate geoengineering, which scatters incoming solar radiation. But a lot of the work we're doing shows that models are overestimating the cooling that should be expected as a result of that method, which implies that, yeah, like first of all, the regional impacts are incredibly under constrained, but then if the models are cooling off too much when we give them this sulfate aerosol forcing, that actually implies that it will be more expensive and more costly and will require more aerosol particles. And so I don't know that it's safe. I guess my attitude about geoengineering is that we should know what we're getting into before we spend a lot of money getting into it.
So we come back to the question of money then, and political will and so forth. So Moshe Vardi early on asked what the impact of the Paris Agreement will be, assuming universal compliance and assuming that maybe the United States will rejoin. Do you have any general thoughts on that?
Yeah, so I can start. So the Paris Agreement is designed to curb temperature change at 2 degrees Celsius, which is considered by climate scientists to be safe warming. So on the graph I showed of global temperature change, we expect based on human decision-making, human activities, human burning of fossil fuels, that lowest emission scenario sets us up for only 2 degrees of global average temperature change. I guess to put that in perspective, once you start hitting 4 to 6 degrees Celsius, which is projected by some of those higher emission scenarios, you start getting areas of the tropics that become uninhabitable, right? This could lead to massive climate refugee crises. And when I say uninhabitable, I'm talking about metabolic heat dissipation for mammals. So we're talking about seriously high temperatures that threaten mammalian life. But in terms of the Paris Agreement, again, yeah, if everybody did exactly what the Paris Agreement laid out, right, again, all of those strategies were designed to curb warming at that 2-degree boundary. And if we were to achieve that, we're avoiding a lot of these elevated risks due to temperature change alone.
So let me follow up on something you raised earlier, Sylvia, which is you noted that we should start planning on mitigation for major flood events. Pedram, you sort of indicate the same thing with your models. Is it wise to invest the money in mitigation, let's say levee systems or such not along the Mississippi, or rather put that money into renewables and try and tackle the problem that face on? How do you see those trade-offs? These are really, that's a tough question. I'm sorry.
Pedram, why don't you go first? You're an engineer.
Yeah. Uh, yeah, well, I think probably we have to use both. I mean, investing money in renewable energy, that would also create jobs. We are going to see shifts in where the jobs would be, and the balance between different sectors. But also, certainly, we need to invest money for mitigation strategies. I think people in around New York after Sandy have been taking it very seriously. And I think we should also think about that more, starting with investing in understanding the impacts of climate change in our region, and also trying to see what we can do. But again, I don't think there is going to be a single solution to any of these problems. And then there are solutions that also there would be a lot of benefit that we can get from them. For example, expanding the renewable energy sector. So I think again, it's a question that doesn't have a single answer, and it would require closer collaboration between people from different disciplines.
Yeah, I totally agree with Pedram, and I would say that in directly answering your question, Rick, yeah, we need to do both. We need to mitigate, which is draw down carbon emissions, and we need to adapt, which means things like increasing resilience of our infrastructure. One thing that I find frustrating, right? It's generally difficult to assign monetary value to ecosystem goods and services, which is a really difficult problem in general in environmental economics. But it's not that difficult to assign monetary values to hurricane damage, flooding damage, right? We have numbers for these things. We know those numbers are going up. We can do a straight up cost benefit analysis for how much we're spending every year on these climate related natural disasters. So I guess I feel I am not sure why those people are doing those analyses, and I think the issue is we desperately need to work with more social scientists and humanists and people who can get this information translated to the people who are making these decisions on the ground. And that's something I've been, I guess, I don't know, I'm thinking about a lot and wondering how to realistically do that. We publish our papers in scientific journals, and who do we call next? But yeah, we do need to be spending the money on both adaptation and mitigation measures if we want, to prevent future, I would say, loss of human life.
Well, I know both of you are fairly active in trying to organize Rice faculty and students to come together to try and do multidisciplinary work to try and address these issues. And so I think it's maybe a small place to start, but I think it's a really important place to start, because you've both said it's important to bring folks to the table who can simultaneously address all the kind of complex questions that need to be faced. The trade-offs between the economy and what we should do, that we know that the science says we should do, those are pretty uncomfortable trade-offs to make. And so it is the witching hour. So I want to thank both of you for a very lively discussion and a very interesting set of lectures. I've certainly learned a lot, and I hope others in the audience have as well. There's still a number of questions out there. I think we've hit most of the topics, but you both might want to answer directly to any of them. And I believe Michelle will be keeping the questions that were asked and sending them on to you. So I want to thank both of you very much for participating and for making this a really wonderful Scientia lecture. Before signing off, I want to note that Jesus Vasello and Kyle Shelton will be speaking on Tuesday, December 4th at 4 p.m. on trade-offs over human housing, which promises to be interesting as well. Again, I want to thank everybody who attended the lecture, and I especially want to thank both Sylvia and Pedram for a very insightful set of comments. So thank you very much, and I believe Michelle may turn us off at this point and quit recording. Again, thanks everybody. Appreciate it.
Thank you.
Be safe.
Thank you.